Good afternoon, everybody. You're a very well-behaved class. Thank you for settling down so quickly. I'm Professor Robert van der Noort, and I'm the acting Vice-Chancellor of the University of Reading. I'm very happy to welcome you here to our biggest lecture theatre for the first of our 2018-19 public lectures. For those of you who haven't been here before or haven't come to the university before, you're very welcome. For those of you who've been here before, welcome back, and we hope to see you more in the rest of the series. You will have noticed that we are filming the proceedings today, and it is live screened. So if you do not wish to appear on the camera, don't look at it. And if you are using Twitter, please join in the debate tonight using the hashtag #UORLectures. Now, I'm delighted to introduce the first lecture of this year's public lecture series, our climate change, past, present and future. Tonight's lecture will be given by Professor Ed Hawkins from the Department of Meteorology and the National Centre for Atmospheric Science. Now, climate change is undoubtedly one of the greatest challenges we will face in the 21st century. Last week's report from the Intergovernmental Panel on Climate Change has warned the world that we have just 12 years left to make the changes to prevent the global temperatures to rise by more than 1.5 degrees Celsius. And the impact of climate change on our weather, which sets new and unwelcome records in many different dimensions, can be observed more and more often. This summer was a reminder of how vulnerable society can be to unusual weather. Overheated buildings, transport disruption, lower crop production, and risk to human health. Such heat waves are hotter as the planet warms. And the planet has warmed largely due to human-caused emission of greenhouse gases. Other consequences of global warming include the more frequent extreme rainfall events and rising sea level as the oceans expand and glaciers melt. And the greater frequency of devastating floods across the world can be nearly read about every day. Now, for several decades now, the University of Reading has been at the forefront of the study of the causes, the extent, and the impact of climate change. And the university has more authors contributing to the sixth assessment report of the Intergovernmental Panel of Climate Change than any other organization in the world, and we are very proud of that. Now, over the next hour, we will learn more about how our climate has already changed, what we might expect to happen in the future, and how society's choices will decide how much further change we can expect. Now, before I pass on to our speaker for tonight, I would like to say a few words about Professor Ed Hawkins. Ed Hawkins is Professor of Climate Science in the National Centre for Atmospheric Science, based in the Department of Meteorology. After gaining his undergraduate degree from the University of Oxford, Ed completed a PhD in astrophysics at the University of Nottingham in 2005, before joining the University of Reading in 2003 and joining the University of Reading in 2005. In 2017, Professor Ed Hawkins was awarded the Royal Meteorological Climate Science Communication Award, and more recently he was awarded the Royal Society Kavli Medal, an annual prize for excellence in science and engineering relevant to the environment. Ed is a lead author for the Intergovernmental Panel on Climate Change 6 Assessment Report and the academic lead for public engagement in the Department of Meteorology and the National Centre for Atmospheric Science, principal research scientist. And finally, you may recall when Ed's climate change spiral was shown at the opening ceremony of the Rio Olympics in 2016. Which makes Ed the only member of University of Reading who made it to the Olympics without breaking into sweat. Ladies and gentlemen, please join me to welcome Professor Ed Hawkins.
Thank you much, Robert, and thank you for coming, everybody. So I hope that you are enjoying this animation while you're waiting for the lecture to start. It's the world in which we live, the very dynamic world. We see the weather patterns moving across the planet in a very dynamic way. You can see why our weather is so variable in the UK. These storms coming across the Atlantic and hitting us from time to time. You can see the hurricanes and the typhoons, which dominate the weather at this time of year in the tropics. We've seen hurricanes hit the US very frequently recently. And in many ways, our society is adapted to the weather in which we live. From the food we grow to how our infrastructure is designed, it affects how our society works. It affects how our ecosystems work. Our crops and our ecosystems are adapted to the weather where we live. So any changes in the weather can potentially cause consequences, negative consequences for how we live our lives and for how ecosystems may adapt. And it's not just the weather where we live. We're a very interconnected world. If we have a heat wave, for example, which reduces grain production in one part of the world, we see bread prices increase all over the world. We live in a very interconnected world. What happens somewhere else is not isolated to that region. So any changes to the weather can have quite negative consequences for all of us. But it's not just the weather that we see changing. It's many other aspects of our climate. So recently I was lucky enough to travel to Greenland in the last summer of 2017 to go on a kayaking trip through the Greenland fjords. And this is a picture I took at the glacier front in southwest Greenland. 5 days kayaking, it was absolutely stunning and beautiful. And we're part of a big group, and we were there sitting on this little rocky island in front of the glacier front, watching and listening. We're there sitting in complete silence, just listening to the glacier groan and move, and just watch it, and listen and feel its energy and its dynamic, movement. It's very static. It's always moving and shifting. And I turned to our guide, who had been guiding kayak trips in that part of the world for a few years, and asked him, have you seen any changes since you've been guiding in this part of the world? This is the 4th year he'd been guiding. I didn't expect that he would say he'd seen very large changes over that time. But he got out his phone and showed me some photographs, which I'm now going to show you. So this is his first kayaking trip to the glacier in 2014. You can see the kayakers enjoying themselves. Focus on the big rock to the sort of centre right of the image. We're going to see that rock in all of the images I'm going to show. So you can see how much ice there is in front of that rock, how high it is. And that was 2014. I'm now going to move on to 2015. Watch that rock. So even in the space of the first year that he'd been guiding, between the first and second year, he'd seen quite dramatic changes, and about half the ice in front of that rock had disappeared. He went back the following summer, and again the amount of ice in front of that rock had disappeared largely again. And then this is the image I took in 2017 when I was there, and you can see the dramatic changes. What was one glacier is now 2. It has split apart, and that 100 metres of ice has just simply vanished in the space of 4 years. So we're seeing changes. Our natural world is telling us that something is happening, that the world is warming, temperatures are increasing, causing ice to melt. And that, of course, all of this ice has melted into the sea to help raise sea levels. So we are seeing the changes. And the little island we are standing on is to the right of this image. And our guide was probably the first person to stand on that island for many centuries, if not thousands of years, on his first trip that summer. But it's not just in Greenland that we're seeing these glaciers melt. We can see this happening all across the world. This is a famous glacier in Austria, sketched in 1885. The glacier is filling the valley. There's a little person at the bottom right for some kind of scale, and you can see how large the glacier is. If you go to that glacier today, you can take photographs such as this. So the sign there measures where the glacier front was in 1995. And you can see how much it's retreated since that time. The glacier has essentially vanished since that sketch was made in 1885. What's even more surprising is if you walk down the valley, like many of these people are doing, you come across a sign like that the glacier was there in 2015, and it's hardly visible at the back of the image. We're seeing the changes. The natural world is telling us the world is warming. And it's not just the glaciers. If we look down on the North Pole, we have satellites that have measured the amount of ice at the North Pole since 1979. And every summer, the ice reaches its annual minimum in September. It goes, waxes and wanes each year. And the minimum time in September this is the amount of sea ice that the satellites see. And over time, you can see that gradually the ice has retreated by about a third, if not a bit more than a third, over the 35, 40 years that the satellites have been observing the Arctic. Or maybe run that once more through. That was this summer in 2018. And of course, again, this part of the world, the animals and the people who live there are adapted to the conditions they're used to having. They're used to having plenty of ice. And so if we're seeing changes to that ice, it's going to have consequences for the people and animals that live in that region. There are, we can see years where the ice is relatively large and where it is relatively small, but the downward trend is unmistakable. And now we're seeing ships pass through the Arctic. Last year, and the last few years, we've seen gas tankers pass through the Arctic to shortcut between Asia and Europe, carrying lots of fuels, gas. And now we're also starting to see cargo ships carrying containers through the Arctic each summer. So people are using the melting ice as a shortcut between Asia and Europe. So the question is, why is this happening? Why are we seeing the natural world respond? Why are we seeing the world warm up? So I'm going to take a brief moment to talk about two of the pieces of the puzzle that were done here in the UK, a long time ago. So on the left we have John Tyndall, who's an Irishman. He lived and worked in London, and on the right we have Guy Callender, another person who was born in Canada but lived most of his life in London. And in the 1820s, scientists were puzzled. They had a couple of big puzzles. They'd recently discovered the existence of ice ages, and they didn't quite understand how the climate could change so much between very, very cold and the climate we see today. They discovered the glaciers had once filled much larger regions in the Alps, for example. And the other puzzle they had was that they couldn't explain why the Earth wasn't a ball of ice. Their calculations said that given the amount of solar energy the planet received, the Earth should be about minus 20 degrees. The Earth should be a ball of ice according to the amount of energy we receive from the sun. But obviously it wasn't a ball of ice. So obviously something was wrong with their theories. And so the idea was that there must be something in the atmosphere acting as a blanket to stop that energy being released to space and to meant the Earth is warmer than perhaps it should be without that blanket. But the question was, what was the blanket? And nobody knew in the 1820s, various ideas. But there was very, very clear observation. There wasn't enough energy coming from the sun to keep the planet warm enough to be habitable. And this is where John Tyndall, the man with the great beard, comes in. So in the 1850s, he started performing some experiments in his laboratory in London. You can go to the Royal Institution today and see some of his equipment still in their laboratories. So you can go and see the big long wooden tube, which I'm about to describe. So this is the experiment. He spent many years perfecting his experiments in the 1850s. And what he wanted to know was, what is it? Is it a gas in the atmosphere which is enabling the atmosphere to act as a blanket? And to do that, he had two sources of energy. He had two sources of heat on the left and on the right of the picture. And one of those sources of heat passed through a long wooden tube, which you can see there, horizontal tube, ending up in the middle with this sort of horn-shaped device. And we had another source of heat on the left-hand side. And he was able to measure the temperature difference at the point in the middle. And what he was able to do was to fill the tube with different gases and see if that had a difference, had an effect on the temperature measured in the middle. And he tried lots of different gases. And he very quickly realised there were a few which absorbed the heat, absorbed the infrared radiation coming from the right-hand side. And those gases were carbon dioxide, methane, water vapour. And he very quickly realised that these gases are the ones that act as a blanket and keep our planet warm. He simply discovered the greenhouse effect. So these gases absorb infrared radiation, act as that blanket and keep us warm. So the greenhouse effect is a good thing, right? It makes the planet habitable. It means that we're not a ball of ice. It means we live on a planet where we have oceans, for example. And in his paper in 1861 describing these experiments, he said, if we see changes in any of these constituents that I've identified, we will see changes in our climate. We knew this in 1861. And of course, he wasn't actually talking about human activity at that point. He was trying to explain the temperature of the planet and also the causes of the ice ages. Human activity was not mentioned in any of his work. He was merely trying to explain the world around him. It took a few years later, in the 1880s and 90s, we started to think about human activity a bit more. We started to burn fossil fuels, adding carbon dioxide to the atmosphere, changing the constituents of the atmosphere, enhancing the natural greenhouse effect, making it larger. And so there were theories in the 1890s about how much would the Earth warm if we doubled the amount of carbon dioxide in the atmosphere. We're starting to ask the big questions. And the answer was they came up with about 4 degrees. They worked this out in the 1890s. But at that point, we weren't burning enough fossil fuels to see a difference. They thought it would take hundreds of years for us to have a noticeable effect. And so the theory was sort of often a bit forgotten because, it doesn't matter, it's hundreds of years in the future till we can be able to see an effect. What they didn't foresee was the rapid growth in our burning of fossil fuels. And so that's where the second character in our tale comes in. So it took many years, but in the 1930s, we started to notice that the world was warming. And this chap, Guy Callendar, who was a steam engineer and a very keen amateur meteorologist, he collected temperature data from 147 locations around the world and put them together to come up with an estimate of how much the globe had warmed. And this is his hand-drawn graph from his study in 1938. No computers, had to do all the calculations by hand, very tedious, very boring, but that's what he did. And he drew this graph and presented it to the Royal Meteorological Society in London in 1938. And you can see the temperature warming up. Focus on the bottom line. So between 1881 and 1935, he observed that temperatures had increased by about 0.3 degrees over the land areas where he had the data. Very widespread distribution of data he managed to get hold of at that time. But the even more interesting thing is what's in the top right-hand corner of the diagram. There's a little dashed line labelled CO2 effect. So as well as being the first person to demonstrate that the world was warming, he'd also demonstrated that the amount of carbon dioxide in the atmosphere had increased. He took very scattered observations and realised that actually we could detect the increase in carbon dioxide in our atmosphere from the burning of fossil fuels. And he estimated how large the effect on temperature would be of that increase in carbon dioxide. And he estimated it about half what he observed. So he said then, in 1938, we're seeing the effect of carbon dioxide on our temperatures. We had a fully formed theory 80 years ago about why carbon dioxide increases in the atmosphere warm our planet. Did anyone believe him? No. and probably rightly so, actually. We didn't have a complete understanding at that point. It took till the 1950s to have a better understanding of the spectral absorption of the carbon dioxide. Scientists were very worried at that point about whether the carbon dioxide was able to absorb the infrared radiation in the atmosphere. And we had better measurements after the Second World War in the 1950s that said yes, that is possible. Also in the 1950s, we realised that the oceans would not take up all of the carbon dioxide that had been emitted. That was another worry with his theory. And so that was also discounted in the 1950s. And then it started to take him very seriously. And so it was at that point that people started, okay, we need to monitor what's going on. We need to start measuring the amount of carbon dioxide in the atmosphere. And so in the late 1950s, we started measuring carbon dioxide more completely. And we now have a complete record from 1958 to today of what's happened to carbon dioxide in the atmosphere. At that time, it was about 310 parts per million in the atmosphere. We're now about 410 parts per million. And this is set up by Charles David Keeling and is now known as the Keeling Curve. So we see this large increase in the amount of carbon dioxide in the atmosphere. It's also very interesting to notice the wiggles, the ups and downs, the sawtooth. And that's because the natural exchanges of carbon dioxide between the land and the atmosphere. Every northern hemisphere summer, the trees grow, produce leaves, that takes in carbon dioxide from the atmosphere. And then in autumn and winter, those leaves fall, and the carbon dioxide is given back to the atmosphere. So we see this annual fluctuation in the amount of carbon dioxide. But that is dwarfed by the increase in carbon dioxide that we see from fossil fuel production, deforestation, and so on. So we've seen this increase in carbon dioxide. So what's happened to our temperatures? Luckily, we've been measuring temperatures for a very long time as well. So let's start very close to home. Let's start in East Berkshire, a very small part of the planet. But here we are. Here are the temperatures we have from East Berkshire, presented as colours. We started measuring temperatures in East Berkshire in 1864, in Stratfield-Turgis. Anyone from Stratfield-Turgis? Just down the road. So we have temperatures from 1864 up to the present day. And so here we have one stripe for every year in that period, and it's coloured by the temperature in that particular year. The dark blue colours are about 9 degrees for the annual average. That was a cold year back in the late 1800s. A typical year was more like 10 degrees. Since that time, we've seen temperatures increase. We're seeing redder colours, warmer temperatures. And as time has gone on, we've seen annual averages for this part of the world of 11, 12 degrees even, of the warmest years that we've seen in this part of the world. So we can see the temperatures increasing where we live and where we are today. And this picture down at the front here, this is the global picture, starting with 1850 on the left, 2017 on the right. You can come and pick up a postcard and send it if you like later on. So you can actually see quite a lot of resemblance between what's happening at the global level and what's happening in East Berkshire. We see this cold period at the beginning. There are lots of eruptions at that point, cooling temperatures. We can see that in East Berkshire even. And we can see the temperature warming up just like we can all over the globe. But it's not just East Berkshire. If we look across the country, we have 5 different sets of stripes here for 5 different locations across the UK. From Stornoway in the north, Armagh in Northern Ireland, Durham and Sheffield in Northern England, and Oxford close to here. And they're all very similar, independent measurements taken by different people all across the country from the 1880s onwards to today. And they all show the same picture of a warming United Kingdom. A little bit warmer in the 1940s, you can see. Lots of variation from year to year. Blue stripes, red stripes, mixed together to start with. But there's an unmistakable feature towards the end. Redder temperatures, warmer temperatures towards the end. We've seen the UK warm by just over a degree since the late 19th century. And that's not just the UK. We're seeing temperatures rise across the world. Since the end of the 19th century, we've seen temperatures warm across the world, across the oceans and across the land. We see temperatures increase faster over land than over the ocean. We see temperatures in the Arctic warm more than anywhere else. We're seeing 1.5 degrees, 2 degrees, even 3 or 4 degrees in some parts of the Arctic. That's how much warming we've seen already. The oceans warm less because they've got a larger heat capacity. They soak up heat, but the land warms more. So we're seeing the temperature rise all over the planet. 1 or 2 regions don't actually show much warming. They're very interesting. Perhaps we can discuss them at the end. So the bigger picture is that the whole planet as a whole is warming. And so I'm now going to show the spiral diagram that Robert mentioned at the beginning, which is a way of presenting how global temperatures have changed since the 1850s. And it's going to be presented as a circle with the months of the year around the edge, and starting in the middle and moving outwards as the years go and the colours change. So we start in 1850, where temperatures were kind of pre-industrial levels, before the Industrial Revolution. And we see temperatures vary from year to year, a little bit up, a little bit down. And then as we go on, we see the temperatures start to warm, the circles expand as the planet warms. And as we come to today, we see that circle expand very rapidly. We're seeing very rapidly warming temperatures over the last few decades. And the red lines on this diagram are indicative of what the United Nations has agreed are the temperature targets that we would like to restrict global temperature rise to. 1.5 or 2 degrees above those in pre-industrial levels. That's what the the Paris Agreement and the United Nations process has decided it wants to avoid reaching. And we have had some months which would get perilously close to that 1.5 degree line. Now, crossing that line doesn't mean we've breached that agreement. We see variations from year to year. We see hot months, hot years every now and then, but it's just indicative of how close we are to some of these temperature thresholds which the world has decided it would like to avoid. So we're seeing global temperature rises. What else has changed that might matter to people and ecosystems and our infrastructure? So because the world is warming, the oceans are warming, and as seawater warms up, it expands, which means sea levels rise. And as we're seeing, glaciers are melting, adding extra water into the oceans, also causing sea levels to rise. And these two factors have caused around about 25 centimetres of sea level rise since the 1880s. Maybe run that one again. And that rate is speeding up as well. We see the decades labelled on the right-hand side, and the amount that the sea level has risen each decade is starting to get bigger and bigger. So we're expecting this to continue as well, as we'll come on to. So why does sea level rise matter? And why does global temperature rise matter? So we have a picture here from 2017, 3 hurricanes in the West Atlantic. I could have shown a picture from this year as well. It's been another very active summer, as I'm sure you've seen on the news recently, with Michael and Florence hitting the US. So here's Irma, Jose and Katia from last year. So hurricanes have always happened, and they always will happen. But what we're seeing is that the effects of the hurricane on the land are getting worse because of climate change. And there's 2 reasons for that, which we're very confident about. Because we're seeing sea level rises, it means that when the hurricane hits the land, it means the storm surge that comes with that hurricane being higher than it would otherwise have been. The storm is more damaging than it would have been 100 years ago because the sea level has risen. And the other aspect which we're very confident about is because we have a warmer atmosphere holds more moisture, which means there's more moisture with the hurricane, which means it rains more when the hurricane hits land. So we see more flooding because there's more rain, and more flooding because sea levels are higher and the storm surge is greater. We also expect that the fact that hurricanes are coming over warmer water means they will become more intense in future. There's more fuel for the hurricanes to grow. We may see fewer of them, but they will be more intense and come with larger impacts than they would have done 100 years ago, for example. This is how the change in the climate matters to people. It affects the impacts of the events, the normal weather events that we get. Those impacts are worse. Coming closer to home, remember the flooding of the Somerset Levels a few years ago. Hundreds of people flooded in the UK because of the series of storms which swept across the country that year. So again, how has climate change affected this event? And it's a very similar story. Although the set of storms which came across the country, none of them were particularly unusual. You know, we get storms in this part of the world, it's part of our lovely variable weather. But because the atmosphere was warmer, more rain came out of those storms. And because sea levels were higher, the rivers taking the water out to sea were not able to drain as fast. Again, similar to effects, more flooding because we have more rain and we can't drain the rivers as well. Now, of course, there's other human effects. How have we changed the landscape? We're building on the landscape. How are we changing our upland areas? Many other factors come into play. It's not just the climate, but climate has an impact. These storms would have produced less rain had they happened 100 years ago. This is how climate change is affecting us. It affects us through our changes in the weather that we're adapted to. How about this summer? We all remember how hot this summer was. But of course, it was always related to 1976. Famous summer, very hot in the UK in 1976. Lots of talk about, well, was it hotter or was it not in 1976? And I think a lot of those discussions missed some of the broader context of what was going on. Yes, it was very hot here. Yes, it was very hot in 1976. about equally warm, I think the Met Office decided in the end. They couldn't tell the difference. But what really matters is the broader scale context of this heat wave. You know, we may focus on the UK because that's where we live, but there's a much bigger picture we need to think about. So let's zoom out slightly from the UK focus. Let's think about Europe, for example. In 1976, UK and France were very warm that summer, but other places were not. Eastern Europe, for example, Russia, Scandinavia, were actually quite cool that summer. It's the bigger picture. In 1976, we were the unusual part of Europe being so warm, other parts were not. This summer, actually we weren't the worst affected. Other parts of Europe had much hotter than normal temperatures. Sweden, Denmark, Germany, France had far warmer temperatures than normal than we did in the UK. Bigger picture, this summer was much warmer across Europe in 1976. Let's zoom out again and see the whole land. In 1976, we were essentially alone in our little corner of northwest Europe being very, very warm that summer. This summer we were not. We were actually quite cool compared to many parts of the world in terms of whether we were warmer or cooler than normal. We saw heat waves in Japan, in Korea, in the US, across Europe. Greece had these amazing wildfires. It's, again, the bigger picture, the bigger context we see. We're seeing more heat waves across the earth. You know, we can get very focused on where we live, but it's the bigger picture that matters. We're seeing more heat waves, warmer heat waves. And so when we do get the weather, which means we get a heat wave in the UK, the warmer temperatures because of our increase in greenhouse gases means that heat wave is warmer. The effects are larger on our crops, on our infrastructure, our buildings, our railways, our roads, and our human health. We're seeing impacts from those rising temperatures. So how else can we think about what's going on to our planet? Now, ideally, we would like to perform experiments on our planet. Now, you might argue we're performing an experiment on the planet anyway, but we'd like to have a controlled experiment. You know, we'd like lots of Earths on which to experiment and learn about what might happen if we'd made different choices in the past. We can't. We're an observational science. We have to deal with the data we've got and the history we've had. But can we do anything about learning about the past with experiments? So we have to turn to computer models to do experiments on our climate system. So we're going to run a little animation now trying to describe what we mean by a climate model. Of course, it starts with the sun. The sun is the source of all of our energy. It provides the heat to our planet Earth, which we can zoom in on. And what we do when we build our climate model is we split the world up into little boxes, a grid, a mesh, a three-dimensional mesh in the atmosphere in which we can examine the physical equations which govern how the atmosphere and the ocean behaves, and the land as well. We split the whole system up into little boxes and then we understand the equations inside those boxes. So we have to think about equations for the clouds, for example, that flow across the planet. We have to think about what's going on the land surface. We have to think about mountains. How might they affect our weather? How trees, crops, the rivers which flow to the sea, the heat which the ocean gives up to the atmosphere, causing clouds and rain, and how that propagates over the land. We have to think about the factories and the other factors which come into play about air pollution, for example. As well as the land, we have to think about the ocean. We have to think about the currents in the ocean, the upwelling near the coast bringing warmer water to the surface, the ocean eddies which mix the heat around. And we even have to think about the ocean biology. The plankton in the surface waters suck up some of the carbon dioxide, and when that plankton dies, it sinks to depth. So we have equations that try and mimic these processes in our models, in our computer codes. And so we have all of these equations solved on these grids, these boxes, and then we put all these boxes inside a supercomputer. I know, everyone laughs at that. It's not a very good representation of a supercomputer. But anyway, that's what happens. So what does this climate model look like then when we put all those pieces together? So this is trying to mimic that animation we saw at the beginning. That was the real world. This is computer world. This is the water vapour in one of our climate models. Have made a lovely animation. And you can see the water vapour spinning around the planet. There's a lot of similarity to that satellite picture we saw earlier. Our equations and our computer models can simulate the processes and the weather that we get in the real world, and we can simulate them inside a computer. There are no equations or lines of code which say, produce this storm at this time in this location. They are generated spontaneously by the chaotic nature of their atmosphere and the equations that we use. We can see the similarities between our simulated reality and the real world. Of course, they're not perfect by any means, but they can represent some of the key features of the atmosphere and the ocean extremely well. So what are the things we have to think about then when we're maybe thinking about designing our experiments that we might do with these computer models? We have to think about the Earth's orbit, about its spin, its axis, how the orbit might change. We have to think about the clouds, the rain, the ice in the oceans, the ocean circulation, the energy coming from the sun, how that interacts with the atmosphere, the ocean and the land. We have to think about volcanoes that go off periodically. We have to think about factories and the emissions they produce into the atmosphere. We have to think about crops and forests and everything else which goes on in the land surface. And of course we have to think about humans as well. And so if we've got all these factors that we can put inside our computer codes and our computer models, and then we can do our experiments. We can say, well, what would have happened if there had been no humans? So our observations of global temperature show an increase since the 1860s up till today. And our range of computer models which try and simulate what happened over those 150 years, if we take out all of the effects that we know due to human activity, then we can see what our computer models would have done. So this means that we are simulating the effects of the variations in the sun and the volcanic eruptions that we know have happened over that time. And those simulations cannot reproduce what we know has happened. So by the time we get to the 1970s, 1980s, our observations are outside what we would have expected to see had there been no human activity. If we repeat those simulations, but add in all of our known human effects, the greenhouse gases, and actually the particulates from our burning of fossil fuels as well, and the changes in land use and so on, we get a much better match with what's actually happened. We can do these experiments. What if we had no humans? What if we had humans? And see which match our data better. So this is demonstrating, I hope, that our computer simulations can represent what's happened in the past. We can then think about what they might say for the future as well. So that's the past and the present. What about the future? Again, we can think about experiments and choices that we might make for the future. We might make a choice to follow a low carbon dioxide emissions future, or we might think about a high carbon dioxide emissions future. How is that going to affect what happens by the end of the century, for example? These are kind of thought experiments. What if we make one choice or the other? We're not saying necessarily which one we think is going to happen. We're saying these are what we think will happen if these choices are taken or followed. So in the low carbon dioxide emissions future case, which is roughly equivalent to keeping to the Paris Agreement that the United Nations agreed, we are going to see further rises in temperature, but they're far less than if we follow a high carbon dioxide emissions future. And the one on the right is a very, very high emissions future, essentially burn all the coal we can find. That is, 11-degree change in the Arctic, for example, by the end of the century. These are very dramatic changes. Again, we can see more warming over the land than over the oceans, consistent with what we see in the observations. But this is the type of choice we have to make about which future we'd like to live in. And it's not just temperature, of course. It's also about rainfall, for example, one other variable we might be very interested in. Again, in a low carbon dioxide emissions future, we don't see large changes in rainfall in many regions. But if we think about a high CO2 emissions future, we see large increases in rainfall, for example, in the high latitudes in the Arctic for example, and in the tropical Pacific. We also see large decreases of rainfall in areas that are already quite dry, such as the Mediterranean, Central America, and other places. So we also expecting to see changes in rainfall as well as temperature. But it's also changes in things like sea level we might expect to see. Again, because we're having a warmer world, warmer water, seawater expands, the sea levels rise. But how much might they expand in future? Again, we can have these two possible futures. A high emissions future, we might see 50 centimetres to a metre of sea level rise by the end of the century. And if we follow a low carbon dioxide emissions future, we see 30 to 60 centimetres. But there's one other important aspect of this diagram which is important to note. In the last example where we saw the temperature and the rainfall, for example, we have managed, in a low carbon dioxide future, we've managed to stabilise temperatures at a particular level, 1.5, 2 degrees above pre-industrial levels, for example. But the sea level is still increasing. And that's because it takes time for the glaciers, for the ice, and for the oceans to fully adjust to those warmer temperatures. It takes centuries, in fact. And so even in our low carbon dioxide emissions future, we will see sea level rise probably for centuries at a slower rate, but it will continue to rise. If we end up melting Greenland, that's 7 or 8 metres of sea level rise. There's similar amounts in the West Antarctic peninsula also. So these are the types of amount of water that we could potentially add to the ocean to cause our sea levels to rise and flood coastal cities. And we know from looking back at the past, the very deep past, when temperatures were similar to today in the past, maybe a little bit warmer than today in the past, we know sea levels were many tens of metres higher than they are today. We know that this happened in the past, that we lost a lot of the ice at similar temperatures to today. And so in the future we face risks. There's a whole load of risks listed here. Not all of those will affect every part of the world. Some of them may be more severe in many locations than others, but these are the types of risks that we face. We've seen coral bleaching recently in the Great Barrier Reef, for example. Much of the coral reefs are dying for the first time in recorded history because what might seem like a small temperature rise of 1 degree, it means we can reach thresholds in which ecosystems cannot adapt. And this is how small rises in temperature have effects. Wildfires, floods, droughts, and so on. These are the types of risks that we face. So how do we deal with these risks? We have difficult choices to make. We have to choose between whether we want to mitigate those changes, do something about our emissions to reduce those risks. We are going to need to adapt to many of the changes as well. We have very difficult choices to make about energy, diet, land use, the economy, poverty, transport, trade-offs. All of these different things we have to think very hard about. And they're not easy decisions to make about what we do. What choices do we make as a world? They're also expensive decisions. If we think about slightly closer to home, we need to think about whether we replace the Thames barrier to cope with rising sea levels. Tens of billions of pounds to protect London from rising sea levels. When do we do that? Do we need to do that? We need to think about whether we reroute some of our train lines which go near the coast. You may remember the Dawlish railway line which split off Devon and Cornwall, the train link a few years ago when it got washed away. We may need to reroute that around a completely different route, again costing billions of pounds. Do we need to do that? Flood defences or infrastructure changes. These are very expensive things that we might need to change to adapt to our new weather. We're adapted to the weather that we are used to having in the past. We may need to adapt to a different type of weather in the future. So how have our policymakers responded to these risks? So in 2015, the 195 nations came together in Paris to sign the Paris Agreement, and those nations committed to reduce our carbon dioxide emissions to net zero, which means that if we do give off any carbon dioxide emissions, it means we somehow have to capture those emissions to net zero emissions sometime during the 21st century. And as I've hopefully described, how we do that is exceptionally challenging with very, very difficult choices to make. And many people ask, well, what can we do as individuals to help this happen? This has to be an international effort to do this, but what can we do? And I actually think the most important thing is doing what you're doing today and coming here. We need to talk about this issue more. We need to talk about it with our friends and our family and learn more about what the risks and the very difficult choices are. Thank you.
Thank you, Ed. Before I ask the audience, I'd just quite like to know from you: are you an optimist or a pessimist?
I'm an optimist. I think we've responded to challenges in the past, and I think we can respond to this as well. It's not going to be easy. There are very difficult choices, different value systems coming together. How do we weigh up the future of our children and our grandchildren against today? I mean, how do we make those choices? They're very, very difficult, but those are the difficult conversations we need to have. Okay,
so we have a little bit of time for questions. We have a couple of roving microphones. So I'm taking hands and then wait just for a moment till the microphones are with you, otherwise the people who watch online can't hear the question. So, first question. Over here.
Thanks very much for the talk. While I agree that we all need to contribute individually, because that's the only way we're going to do it, be able to have a meaningful impact, it feels somewhat like we're receding into old habits. Give an example, Japan is on course to building 40 new coal power plants, or have 40 operational coal power plants by the next decade, because of what happened in Fukushima in 2011. That just seems mental, considering they've just had the highest recorded temperature in Tokyo. And it begs the question, what meaningful impact can we have when you've got one of the most polluting CO2 emitting fossil fuels being spooled up in there, and places like China, which, again, to sustain their growth that they want, because the world's addicted to growth, how seriously do you feel, from your observations, that nations are actually taking this seriously? Because a lot of the evidence and what we're shown in the media, completely contradicts, say, the Paris Agreement, for example.
Yeah, so in the Paris Agreement, every nation has signed up to reduce its emissions by a certain amount. It's chosen that itself. In the UK, we can only think about what the UK does, but all of those countries have made those promises. They've all signed up to this net zero target. The UK's done remarkably well. I mean, in many ways, it's a world leader. We've reduced our emissions by 40% in the UK already since 1990 levels. We've done the easy bit. We've taken ourselves off coal, and we've dealt with landfill methane emissions. Those are the easy things we've done, but we have reduced our emissions by 40% already. We have our Climate Change Act here, which commits the government to doing more. Other countries, we can't control what they do, but we have to take our own steps. We have opportunities as well. If we can develop technology to help other nations tackle the problem, then that will put us in a good position.
See a hand at the back there.
Hello, thank you for the lecture. With the lecture, I can agree that climate change is real, and the evidence from the recent storms and floods, something that everybody will agree to. But I think the main thing is how do you convince policymakers? For instance, if you are to see the US president, how can you convince him that climate change is real? Thank you.
How do we convince the US president? I mean, it was very interesting. When the IPCC report came out last week, on BBC Newsnight had a American who had advised the Trump presidency before the inauguration, and he openly said that nothing would persuade the administration's mind on this issue, which I thought was an interesting statement to make. But I think in the US, I think what is the very encouraging signs are actually the cities and the states, the individual states and individual cities are making very dramatic actions, California and other places as well. And I think that is how the leadership will come. I think certain states will, again, develop technologies, take those steps, which other states will inevitably follow later on. So there are leaders in the US, and they are making very good steps to reduce emissions.
I had one here, just below, and this one in the middle there. Yes, if you just keep your hand up, then you get microphones near you. So the lady there in the middle.
Thank you, Professor Hawkins. Given that we are completely dependent on the global shipping industry for trade and our very survival, how do you anticipate that the impact of uncertainty about sea levels in the future might impact on the shipping on which we all depend?
So yeah, it's as we see sea levels rise, that is obviously going to affect our ports, particularly. Some of them will be able to adapt to a certain amount of sea level rise, others won't. Maybe we'll need to move some ports. It's not an area that I've thought about particularly. We are seeing changes in shipping through the Arctic, for example. There are cleaner ships coming on as well, I think, to help reduce emissions from shipping. I think that's another important aspect we need to think about. But yeah, we will need to think about all of our infrastructure, ports, cities, anything on the coast, for example, and anything in floodplains as another example. But all of our roads and railways, we need to think about how they will respond to heat, for example. I was on a train which got delayed because of potential track buckling this summer, and I'm sure many others were as well. So we have to think about how we adapt our infrastructure, be it ports or anything else, to the new weather that we will have.
Following on from the previous question, how do we persuade the US administration to talk sense about climate change? How do we persuade our local politicians in this area to talk sense about climate change? For example, Wokingham, John Redwood, he's many times spoken with me, explaining that climate change is a complete nonsense and it's a socialist plot to undermine normal business processes. What can we do about that?
So voting and talking are two very key aspects. We have to keep talking, if we make this an issue which people talk about more regularly, like we talk about schools or hospitals as big topics which we care about a lot. If we make climate change one of those topics as well, it will gradually bubble up as an important issue, which politicians may take seriously. We have to keep asking questions to our politicians more regularly than we do. It was not a topic that was much discussed in recent UK elections, for example. If we can make those questions, journalists put those questions to politicians, it will start, that conversation will start about what we do about it, rather than when it's real or not. I think if someone thinks there's a socialist plot, as you described, then I think that's the reason I like to focus on the history and the fact that we've known this for a very, very long time indeed. It's not some modern environmental crusade. It is something we've understood the basic physics of for 150 years. We knew the world was warming in 1938. We knew the reasons, and by the 1970s and 80s, it was very clear in our observations that we were moving outside the range of what we would expect otherwise. That very long history, I think, is very important. that it's basic physics and chemistry at the end of the day that describes that if you add carbon dioxide to the atmosphere, it will warm up.
I've picked up 4 more hands. So there's one in the middle there, Anastasia. Then Charlotte, I've got one here, just on the second row. So we'll take that one first.
Hello. Even amongst countries and states and organisations that accept the reality of climate change, there seems to be very little understanding about the necessary solutions. IPCC Working Group 3, I know they've come out with a new report, I haven't looked at that one much yet, but the last one and previous ones have all come to the conclusion that we need renewables, nuclear and carbon capture and storage, and yet countries such as Germany and states such as California that are supposedly held up as paragons of action on climate change are actually rejecting the scientific consensus on mitigation and are moving backwards. Germany has abandoned its commitments under the Paris Agreement to reducing its emissions and is bulldozing ancient forests and villages, burning more lignite, which is killing thousands of people across Europe and hundreds in Britain from air pollution alone, let alone the effects of climate change. How do we get that discussion going and communicate the scientific realities of what we need to do for mitigation?
There's a lot of very similar questions. I mean, as scientists, our job is to communicate those risks, which I think we've done as clearly as we possibly can. We've been very explicit about the risks, about the changes that would be necessary to meet the targets that the countries have set themselves to limit emissions. Again, we can all do our own little things, but I think, as I'll come back to again, we need to talk about the issue more. We need to talk about the very difficult choices we have to make. What energy mix do we have? What do we do about transport? All of these very, very difficult choices that need to be made. They can be expensive, and so there may be a reaction against that. How do we value our future generations? These are not easy questions, and we have to keep talking about it and raise it up the political agenda, and make it become a topic which we talk about a lot more, and it becomes as important as many other topics. And if people start voting with that in mind, then the politicians will follow. But yeah, I agree. It can seem very frustrating, but that's what we have to do.
Right. A lot of talk about carbon dioxide at the moment, and we're getting into politics rather than the subject matter. 2 things. It's sort of mentioned that this was going to talk about the history of things. History didn't start about 150 years ago. It started a very long time ago. We've had ice ages,
Yes.
mentioned briefly,
Yep.
and rapid climate change, mentioned in one sentence. How do you link that together? That's the first question. The second one is, we're so busy worrying about carbon dioxide, we tend to have forgotten about methane.
Mm-hmm.
Can you say something about that?
No, two good questions. So, I can't fit everything in one talk, right? So, as I described very briefly, back in the 1820s, we discovered ice ages, and we wanted to understand them. So, we know that every roughly 100,000 years or so, the Earth goes through a cycle, or the last million years it has done anyway. It goes from what we call now an interglacial, which is what we're in at the moment, and to about 4 degrees colder in an ice age, and we know that's due to the Earth's orbit changing subtly. That's what initiates those ice ages, and there are other feedbacks such as carbon dioxide and water which follow and amplify those small changes. So we know we have some understanding of the causes of those, and we certainly do think about them very, very carefully. What we're seeing now is unusual, right? We are pushing the system outside what it's seen before, but we have to, you're right, we have to understand and learn about those past changes as well. We have a lot of people doing that. It's not an area that I focus on particularly. Methane is also very, very important. It's the second most important greenhouse gas. It's not as long, it is per molecule, it's more powerful than carbon dioxide. It's just there's less of it in the atmosphere. So that's why it's less important. But the changes in it are very important. So we're seeing quite large increases in methane over the last few years in the atmosphere. and we think that's coming from the tropical wetlands. As they're warming up, they're emitting more methane. We do worry a little bit about Arctic changes in methane. We know there's a lot of methane stored in the permafrost and in the deep ocean. So we do think about that, we do worry about that. At the moment, there's not much evidence that the Arctic methane is entering the atmosphere. Too much of it is entering the atmosphere at the moment. We're seeing the chemistry of the methane in the atmosphere is telling us it's coming from the tropics, this increase at the moment. But that risk is there, that those large sources of methane could come out. Again, that's one of the harder things that we understand slightly less well than other things, the methane problem in the Arctic, I think. Although, there was a big research program recently on methane, and I think that concluded that a lot of the methane that might come out of the ocean in the Arctic, in the deep ocean, might actually dissolve in the water on its way up, and so not actually reach the atmosphere. So there's hints that it may not be quite as bad as the worst case, but there's still more to do on the methane problem. There's Keith Shine here is a world expert on methane, if you want to go and talk to him afterwards.
I had one at the penultimate row, the gentleman with all his hand up there. From the other side.
Hello. How can you help governments change their policy of funding? Because at the moment they're funding polluters because they believe that businesses create wealth instead of just transferring wealth from customers to business owners.
I'm not sure it's my job to do that, unfortunately. I think in the UK, we, as I say, we have reduced our emissions in the UK while growing our economy. It can be done. That we decouple those two things, but we need to talk to businesses more about what they are vulnerable to. Every business will be affected by changes in the weather in different ways. From an ice cream business to a train company or a mobile phone company or any of our big industry will be affected by the changes in the weather, and we have to talk to them about how those changes in the weather might affect their business. What type of weather situations are they? Do they start losing money or earning money? And start talking to them about, are the changes we're going to see in future opportunities, or are they risks to their business? And then they can start thinking about the actions they might like to take.
Ladies and gentlemen, I think we're running out of time, and we're getting to the people who quite like to go home because they're working here. But and before I want to thank Ed, I just want to say the next public lecture is on the 23rd of November. It's delivered by Rosa Friedman, Professor in Law on Human Rights, Global Wrongs, the Universal Declaration of Human Rights at 70. Just back to tonight, as you would expect from somebody who has really built a reputation on making climate change visible to us, not just at a global scale, but also sometimes at a more local scale that we can relate to. You've probably done the world a huge service by just drawing people's attention to the simple stripes and the spirals that actually make us understand what is really happening, because your own experience doesn't always think along the 150-year time frame. And I think for that and for this superb lecture, thank you very much, Ed.
Thank you. Thank you. Thank you. Thank you.